Hello, physics kids. Gonna do the third left-hand rule today and try to make it simple, but this governs so many things. This puts together for us how our modern world is powered. It governs power generation, how when we simply rotate, so a wire goes through a magnetic field, it forces electrons to move along the wire. Power generation, it causes electric motors to work. How when we have electricity going through a coil and it's in a magnetic field, it causes the coil to rotate. It's how old-style TVs work, how you can take an electron beam and move it around a screen using magnetic fields. Third left-hand rule is responsible also for one of the most significant things we have, these things. What up till now I referred to as a magic box. Here would be another one. When you open them up, there are coils inside. It's this. If you look closely, there's writing here. This writing says input, 110 volts, output, 9 volts. How do you take 110 volts, which would melt a device that only needed 9 volts, and turn it into a safe 9 volts at the other end? These magic boxes aren't going to be magic boxes anymore. Now they're transformers, and we use the same rule. The third left-hand rule of electricity governs how all of these amazing things work. In any computer, you have a power supply. That power supply will convert that electricity coming in at a high voltage that would kill a computer. Are bells ringing for you on this? Are you getting this yet? It would kill a computer and turn it into a lower voltage that can power a computer. Not many of our devices are really designed for the 110, 120 volts coming out of the outlets. Most all devices have a power converter called a transformer. If you look on the telephone poles outside, many of them have a big can on them. What's the can about? You know they're ubiquitous, everywhere. What's the can about? Well, that's a transformer. That will convert the 4,800 volts carried on those topmost lines. That's extremely dangerous. Why would we carry at such a high voltage electricity around? Well, we have a variety of ways of explaining it. So why don't we get into it? First, let's cover the third left-hand rule. It's really very basic, but it's the hardest of the left-hand rules because instead of 2 variables, now we have 3 variables. So, third left-hand rule, we start with a magnetic field. So here we have one north to south. Third left-hand rule says, fingers in direction, we'll just say magnetic field. So fingers point in direction of magnetic field. Thumb points in direction of electron flow. And now, the palm of your hand is in the direction of deflection force, or the force on that electron. So let's consider. If we have the magnetic field going this way, so my fingers, check, left hand, that's good. So my fingers are pointing in the direction of electron or a magnetic field. Now I'm going to use this to be my current carrying conductor, my wire. And if the electrons are flowing towards you here, so my thumb is pointing towards you, then this wire would be deflected down if the electrons are flowing towards you. If the electrons aren't flowing at all, and I'd like them to flow towards you, all I have to do is take this conductor and push it down. And that will make electrons flow in the wire. So you can see this is the magic behind all our electrical generation, or most of it anyway. All we're doing is taking a wire, pushing it through a magnetic field. Now you realize we want to go as directly through the magnetic field as we can. If we went diagonally, only the component of that diagonal line that would represent going directly through would be actually doing the generation. So we want it to really be going directly through. So we have this in two ways. If the magnetic field going this way and I push the wire down, I generate a flow. If there's already a flow towards you in this, well, the palm indicates that that wire itself would be pulled down. So that's where you get off with the understanding that a motor and a generator are the same device. A motor can be both a generator, a motor can be, or a generator can be a motor. Thus, in these two things, when I turn this one handle, the other turns. This is acting as a generator when I'm turning it. This is acting as a motor when I'm supplying electricity to it. And I can reverse that. So it's the same exact idea. They're both using the third left-hand rule. Okay? So right away we have some tremendous use there. Our whole civilization clearly, to a large extent, is based on this. We also have this thing going on called alternating current electricity. Now, if I have a battery, that battery is direct current. One side is negative, one side is positive, and current just flows from negative to positive. You could do things with that. But with alternating current, there's something else going on completely. Imagine the power company, it has, let's think of it as plumbing. It has two pipes going to you, alternating back and forth. It pushes on one and pulls on another. So it pushes the water towards you on one pipe, pulls the water towards it on the other pipe. Now imagine that being hooked to some cylinders in some simple machine, a washing machine whose tub is going to go back and forth. Well, if they do that, push, pull, you can imagine it would be pretty easy to get the washing machine to work with that. As a decent analogy, that works for what's going on with power that they're sending us. But why would we do AC? There's a tremendously wonderful reason why we would do AC. And it also has to do with this. It's a little bit more complex, but we can skip over, fortunately, a lot of the complexity and just get right to the heart of the matter. When we're talking about a transformer, we'd be talking about, here is the iron core of a transformer, right? We want the domains to be working in this. So if we hit this with a magnetic field, the domains will line up. So what we do is we have a coil of wire that would be the primary coil. And the electrons would wrap around this primary coil. And the more coils, the better. Let's say there's 100 turns here. And now on the secondary coil, the secondary wraps here. Let's say we have fewer turns on this. Let's say we have 50 turns on the secondary coil. Now here's what's going to happen. As we get our first pulse of AC here, the current is coming this way, and we generate a magnetic field that wraps around, and as the magnetic field passes through that secondary coil, it generates a current in the secondary coil. Then we turn off the current, so we shut the current down. Now, again, as the magnetic field shuts down, current is again induced in that second coil. Okay, so the current here is creating a current there. Pretty cool. But the voltage is key, and the voltage we get at by this equation. The secondary turns divided by the primary turns, and this would really be the number of secondary turns over the number of primary turns. Well, what happens here? Well, if I had 100 turns on the primary and 50 turns on the secondary, so we have 50 over 100, it would reduce my voltage by half. Whatever the input voltage is, now the output voltage would be half of that. And that's how a transformer works. They all work the same way. They all have these two coils of wire in them. And the two coils of wire are entirely separate. If you unwind it, there's no connection from the first wire to the second wire. The connection happens through the magnetic field, and that allows you to change the voltage. You could step the voltage up, or you could step the voltage down. So why do we do this? Well, you can imagine 110 volts applied to your phone will cause your phone to burst into flame and crisp up. It's not going to work so well after that. There's a whole lot of devices that 110 volts is way too much for. Your vacuum cleaner, your dishwasher, those work great at 110 volts. But your phone, all the little tiny devices you have, those won't work at 110 volts. They'll just burn. So to reduce the voltage tremendously would be wonderful. But what's the deal on the telephone poles? Why do we have that on the telephone poles? And here we need a little bit more physics, so bear with me on this. The whole thing is, we make the power usually a long distance away. This school uses a lot of power. We're not making any of it here. We're making it could be hundreds of miles away at the power generating plants. So we have to transmit it here, and we transmit it here on these wires. So are we going to lose some on the wires? Well, the wires offer some resistance. So we lose a little bit of power as we transmit it. So let's talk about this for a second. The power, we know, is equal to voltage times current, V times I. But voltage, we remember resistance is voltage over current. Resistance is how much electrical pressure you need to apply to get a certain current. Well, if I solve this for V, I get IR, right? V equals IR. So if I put that here, I, R, I, we could simplify that by saying I squared R. The power is equal to the square of the current multiplied by the resistance. Okay, we're talking the power you lose in the wire is the resistance times the square of the current. So if I could decrease the resistance of that wire, that would save some power. So what could I do to do that? Well, I could make the wires out of silver. You know, why aren't we going to do that? Doesn't take a genius to go that would be a little pricey. Well, then I could make the wires much, much thicker. Again, a little pricey, not just in a much more expensive wire, but much, much larger and sturdier transmission towers to hold such a heavy wire. Plus, when you snow on it or you apply wind to it, it's going to be a more difficult wire to deal with. So the transmission towers have to be even stronger. Plus, the resistance isn't that big a deal compared to, well, the current. The current is going to be the big player because it's the square of the current. So if you double the current, you quadruple the amount of power you lose. So what we want to do is lower the current as much as we can. So we go back to our original formula here. Power equals voltage times current. So we don't care, as long as the power is staying constant, we can vary these two things. So how can I lower the current? Well, by increasing the voltage. So if I increase that voltage, I'm going to lower the current. And that's what we do. When you have a power generation station, we put it through that transformer and we step it up. So we might make the voltage 10 times, 100 times greater than the voltage being produced. Well, that would make the current 100 times less. Now, yes, there's going to be a little bit of loss, but still, it's going to make the current enormously less. And then we send that high voltage electricity to wherever we're distributing it. Now, high voltage, is that dangerous? Yes, high voltage is really, really dangerous. Why? Well, if you have a really high voltage line near you and you're even standing next to it, you can arc right through the air and fry yourself. Well, take a look at those transmission towers. The higher the voltage, the bigger the towers, the more they keep those lines away from everything. Those lines don't even have insulation on them because it wouldn't really matter. That arc would go right through that insulation if you got close enough. Those towers keep those lines separated with a bunch of ceramic discs. Each ceramic disc, they're more or less the same. Each ceramic disc is rated at 15 kilovolts. So 15,000 volts per ceramic disc. So you can count the ceramic discs and find out roughly what the voltage is on that line. Those lines then send a tremendously high voltage to us, but we can't use that tremendously high voltage. We certainly couldn't put them even on our telephone poles at that tremendously high voltage. So they go to a substation where they have step-down transformers, and they drop the voltage. When the voltage gets out on the transmission lines on the telephone poles, it's generally 4,800 volts. If you touch that, you will explode. So again, it's really dangerous. That's why they're on the top. They're the top lines on the telephone poles. We worry about them. If they should come down, we send the trucks out to fix them. They have circuit breakers to turn them off if they should fail and hit the ground. If you ever see a live one on the ground, it'll be melting the pavement it's touching. You need to always avoid them at all costs. So, what do we do from there? Well, that's what the can on the telephone pole is between you and that high voltage wire. That can drops the voltage down to a voltage that you can then bring into your house. That is a much lower voltage. The 120 volts you're generally using in your house, that's not going to arc through wires and such. That's a much more reasonable voltage. Still lethal voltage, you still have to be incredibly careful with it, but it's not going to do the complete unexpected. And we have safety precautions that we have built into the house in order to deal with that. So, third left-hand rule allows us to manipulate electricity on an unprecedented level, and it gives us our modern way of life in the most beautiful and coolest ways. I hope this helps. There's a whole bunch of other videos you can look at online all about power transmission. There are some of the coolest and most interesting jobs in the power transmission industry, from being a lineman to people who are the engineers who design this stuff and design the next generation of materials that keep us all powered and safe. And if nothing else, it is a fascinating behind-the-scenes world that we all need. You never think about a lineman until the lights go out. And then a lineman is the only one who can save you. So there's a lot going on here, and it is fascinating beyond words. But we use third left-hand rule all over the place. Pretty cool. Hope you learned it a little bit, and see you next time. Thanks for watching. Bye-bye.